Okay. Just a moment, team. Okay. Just a moment. Excuse me. All right. So I was saying that we were asking ourselves the question that where do the storage resources used by virtual machines come from? We try to look at the different underlying storage resources where our virtual machines can actually pick or get storage facilities. Let me try to mute some of you because I'm getting feedback. So we went ahead and we looked at the storage architecture for virtualization, where we said we have virtualized storage and non-virtualized storage. And when we looked at virtualized storage, we looked at these two architectures. We looked at the network attached storage, which we are calling the NAS, and also we looked at the SAN. Okay. We looked at SAN, and also we tried to understand that NAS is a file level based system and SAN is a block level system. And we tried to also understand that there are some underlying hard disks which are now raided to come up with some kind of storage pool. And depending on the architecture, we can have already a file system on it, or we already have a logical volume on top of that. And then we have our file system, and then we come up with our shared pool where our virtual machines are able to create their hard disks to use. We also looked at the non-virtualized storage, where we so that we can have our typical underlying hardware resources, and on top of that we can either add our logical division, or we can come up with a distributed storage pool, pulling these resources together. I repeat, distributed storage pool, and add our logical division, where we create our logical unit numbers or the logical volumes, and then our virtual machines can access and use the storage resources. Still, we went ahead and looked at the virtualized conversion path in cloud computing, and we saw we have our underlying infrastructure here, which is now raided or replicated and put together into a physical volume, which physical volume also now we create our logical volume, which logical volume now, based on the file system you're using, either if you're using the network file system, we can attach these and or format them to the format that is understandable in our cluster, and then we have our virtual file system to create our shared catalog. And we said in our non-virtualized conversion path of cloud computing, we can either use RAID or replication, and we come up with our physical volume and then create our logical divisions, and then we have our logical volumes, which are now attached to the cluster, and then we have the resources for our virtualized environment. So we looked at the different disks. I'm not going to talk so much about them, but SATA and SAS, and we looked at nearline disks. Also looked at SSDs. We also tried to compare the different types of hard disks and their speeds in terms of performance and the price. We looked at centralized storage, and we had yet to look at distributed storage. We looked at centralized storage, and we have one kind of disk enclosure, a centralized kind of storage, and we have all our servers accessing our storage, which is either raided to create a storage pool, and then our different servers are reading and writing data from that storage pool. So we went ahead and looked at raiding, because we're talking about raiding, and we said it helps us to be more efficient and also to help protect our data. And because we have different RAID levels, and where we talked about RAID, and we said it is just an array of independent disks which are put together to come up with some kind of logical disks. Okay, so we looked at RAID 0, and we said this is also called stripping, and it does not have data redundancy, though it gives us the highest storage performance. We also looked at RAID 1 and we said this one is also called mirroring. It mirrors whatever is here, it mirrors them to that disk, and it also gives us redundancy, but then it has low storage performance since the total capacity in this RAID will be the total capacity of one drive. Of the actually the smallest drive. So we also looked at RAID 5 and we saw that RAID 5 tries to balance the storage performance and also the redundancy, and gives us a redundancy of one disk, and it uses parity checks to restore the data in case one disk fails. And also looked at RAID 6 where it gives us a redundancy of two disks. It uses parity check and an independent parity check to help us repair and restore the data. It gives us a redundancy of two disks. Still, we looked at SUN already, and we looked at NAS, and we said NAS is a block level kind of it's a block level kind of system, and we said we can access it either using IP, which leads us to IP SUN. We can access it in fiber channel, which SUN through the fiber, or there's another one called the fiber channel over Ethernet, and they're still working to improve on it. We also looked at NAS, and we are saying NAS has some kind of file systems, and we have our CIFS and NFS, and we also have the SMB, the small message block by Microsoft. These are some of the common file systems that are used in SUN. So we looked at that in case you're using a Windows Server to access our SUN storage here, or a Unix server, like a Unix-like server to access using the network file system or the common internet file system. So depending on the different types of file systems that are available, we can be able to access these guys. So this is a file-based file system, and this is a block level file system. That is maybe the key major difference I would love you to get from today's lecture. So let us now try and look at distributed storage. What comes to your mind when you hear the word distributed? Anyone else? Anyone to tell us something about distributed?
Different locations.
Different locations. Okay, that qualifies. This is Wilson, eh? Or
Yeah.
Peter. Wilson, thank you, Wilson. So with distributed storage, we are saying that distributed storage is quite different from the conventional storage. What it does, it virtualizes all the available space which are distributed across different hosts into a single virtual device. So the data stored in the virtual storage is also distributed all over the virtual network. So like the way you can see these different servers, like commodity x86 servers, we can have the storage resources in a distributed storage system coming from these different servers you're seeing here. The server A, the server B, the server C, and the server D. So we can have different resources coming from those servers, and a distributed storage system has no controller or disk enclosures. Like you saw the other one, it had a disk enclosure in the middle, and all other servers, all other systems are accessing that disk enclosures. So what happens here, the clients delivered by the distributed storage system are responsible for all the following: to identify and manage hard disks, to establish routes, and also to execute the different input and outputs. So the distributed clients mode has both advantages and disadvantages. So we are seeing here that in our distributed storage system, we have our servers here, the different servers, and as you can see, we are going to get all. Remember, now these servers have hard disks inside them. You have disks on your network. All these machines, let's say, are connected on your network, and now you want to leverage and get storage from them. So you will read or replicate the disks that are available on these servers after you create your storage pool. And after creating your storage pool, after you do your replication, you have your distributed storage pool where now different servers write and read data from this distributed storage pool. And we're going to see some of the advantages that come with this kind of the storage architecture. So you have already seen that we have different clients or CNAs, or you can call them hosts or servers, that are going to come and give resources, the storage resources to this, and therefore replicate that drives, and then we come up with our distributed storage pool. So we are saying here that in terms of capacity expansion, any server, the one with the commodity x86 architecture, having a client installed on it, like for example in Fusion Compute you install CNA client, it can be a part of the distributed system. So therefore this mode helps us to deliver scalability. By scalability I mean I can just get my other server here, place it, install a client on it, and then I'm able to leverage and take advantage of the storage devices that are in here, and it also acts as a storage pool. It also contributes to the storage pool, thereby expanding it, and other applications can be able to read and write data on it. So in addition to the applications running on the server, the client software installed on the server also consumes compute resources. So when you plan a distributed storage system, you must reserve certain amounts of compute resources on servers you intend to add to this system. So this mode has certain requirements in the hardware resources of the server. So in a traditional centralized system, data is read and written by controllers. So the number of controllers is limited. So in a distributed storage system, any server with clients can read and write data. This improves, one, the input and output of some to some extent, because a distributed storage system does not have controller bottlenecks, that exist in centralized systems. So the path of reading and writing data need to be calculated repeatedly, or do not need to be calculated repeatedly. Just excuse me, just a moment. Coding. Okay, so to ensure high availability and security of data, the centralized system uses the RAID technology, and RAID can be implemented by hardware and software. So all drives in the same RAID array, regardless of software or hardware implementation, must reside on the same server. And that's why we're saying that RAID requires a unified RAID card, and storage RAID requires a unified operating system. And because of the hard drives of a distributed storage system are distributed across different servers, the RAID mechanism cannot be used in such a system. Therefore, we use what we are calling the replication mechanism. And the replication mechanism is typically used in distributed storage systems to ensure high data reliability. What replication does, it keeps identical copies of data on different servers. So the failure of a single server will not cause data loss. The distributed storage system combines local disk of all servers into several resource pools based on the resource pools available, and the distributed system delivers interfaces for creating and deleting application volumes and snapshots. So what you're trying to say here, that it is hard. Remember, for you to be able to RAID, to come up with your RAID, you need to have one enclosure, or you need to RAID disks in a single disk enclosure, that disk array. And we are saying they must reserve, but since you're using distributed and they're all different disks are located on different CNAs or hosts across our network, it is hard for us to use the RAID mechanism. And that's why, to protect our data, we are now coming up with this term, which we are calling replication, to help us have some kind of security for our data. And this is effected through creating identical copies of data on different servers, and that entirely depends on the kind of configuration that you are going to put up when you're creating that kind of storage pool. So the distributed storage system combines local disk of all servers into several resource pools. Just like you see here, we have different servers. It's going to combine its disks, all the disks here, replicate them, and then we come up with our distributed storage pool. So based on the resource pools, the distributed storage system delivers interfaces for creating, deleting application volumes, and also snapshots. And it also delivers volume device functions for upper layer software. So what we are saying that in a distributed system, each hard drive is divided into several partitions, and each partition belongs to only one resource pool. And a partition functions as a data copy. So the system ensures that multiple data copies are distributed on different servers. When the number of servers is greater than the number of data copies and data consistency between multiple data copies, then the data in the partition is stored as key value pairs. So I'm just reading through some of these things because I'm just reading through some of these things, and I advise you can also get some time and read through them. But the distributed storage system delivers volume of the upper layer, which is easy to use. The system ensures that the number of active partition is the same as that of standby partition. So what distributed system does, or for it to be able to effect the replication and put the identical files on the different disks, what it does it creates partitions from different disks, and these different partitions are what we are calling data all identical or key value pairs, which store that data from the different hard disks. So we are saying here that someone is unmuting. I'm muting them and they are muting. I don't know why. Okay, so let us continue. So we are saying here we are going to replicate our disks from the different servers. After replicating those different disks from different servers, then we have our distributed resource pool. Now, as we are writing data, let me just rewind just a bit. If we are writing data in our distributed storage resource pool, we are going to come up with our data, or let's say the end user is going to write the data. Our data comes to our distributed storage pool, and then boom, that data is replicated, yeah, to the different number of partitions. Because you see now we created 3 different resources, so our data is going to be replicated, and that data will be stored accordingly to the different partitions that we have in our replication mechanism. Okay, so let us also see when we are going to read data. So when you're reading that data from the pool, it will read from one of the partition, then it is actually able to give the data to the end users. So these are some of the common distributed storage products. We have this, we have the one for Fusion storage for Huawei, we have this, we have also that for vSAN for VMware. All right. So let us look at virtualized storage versus non-virtualized storage. And we are looking at just the path. In virtualized storage conversion path, we have already looked at this, and I'm not going to focus so much on it. We have been explaining it, format it to the file system, and then we attach it and format it to the file system that is readable by the cluster. We have our virtual file system, and then we have our catalog. Then in a non-virtualized conversion path, we have our disks, which we are going to read or replicate. then we have our physical volume, then we have our logical volume, and then our logical volume is attached to a compute cluster, and then we are able to use those resources that we have been already explaining. So here we are saying that array can be seen as a large physical volume made up of a number of disks. I've already looked at this, and on top of a physical volume, you can create one or more logical units of specified capacities. So the logical units are called logic unit numbers and can be mapped to hosts as basic block devices. So we're looking at the relationship between RAIDs and the logical unit numbers. Okay, so we're looking at the relationship between that and the logical unit number. So we can create a logical unit number on a single physical volume, and we can also create multiple logical volumes on a single physical volume. But when you're saying logical volumes, most of you people say, I'm going to partition my hard disk, I'm going to partition my hard disk, but yet actually in reality you're creating physical volumes on your you're creating logical volumes on top of your physical volumes, and that creates your logical unit number, or what you're calling logical volumes, or what you're calling partitions in our normal layman language. So the process of creating a logical unit number, we have our hard disks, we either RAID them and we come up with a physical volume. We can choose to, after RAIDing, of course, segments are created, and then we have our logical division, which creates our logical unit numbers, or unit number, sorry. So, and then we have our logical volume. We looked at common file systems, the NAS file system, and also the file system in an operating system. At the beginning of yesterday's chapter, you gave me some examples of the file systems in an operating system. Now, can I get someone who can tell me about some of the common file system in a NAS file system? Any volunteer? We have been mentioning them. Anyone?
NFS.
NFS. Yes.
Then we have the CIFS also, I think.
You're just thinking, or you're
I'm sure.
You're sure? Yeah, okay, that sounds better. Okay, what else?
SMB.
SMB. Okay. All right. And some of the file systems in an operating system?
FAT32, NTFS.
NTFS, FAT32, and so on, and so on.
XFAT.
XFAT. Okay.
Yeah.
All right. So, okay, FAT32, XFAT, and so on, and so forth. Let me see if I have anything on the chat. I said the topic was as if from MIT. I don't know what you're trying to mean, but let us try to continue. So we are saying that I'm trying to see here. Let me see. We are on the screen, right? It is fine now. Okay, I think there's nothing for me in the chat. Okay, so let me just go back to our previous slide, this one, where we're trying to look at the difference between virtualized storage and non-virtualized storage. So let me just go through these some of these content. As we are saying that virtualized Storage virtualization described in what this chapter, which we have been looking at, refers to virtualization in a narrow sense. So if a cluster has a file system, it is a virtualized storage. So the moment we have a cluster and it has a file system already, it's a virtualized storage. Otherwise, if it does not have a file system, then it is a non-virtualized storage. So the file system can be a NFS, take note of that, or a virtual cluster file system. So it can be an NFS or a virtual cluster file system. So if no file system is available, then the virtualized cluster needs to directly invoke logical volumes that are found within your storage architecture. So we know that the physical disks reside at the bottom. Here we said we already know that the physical disks reside at the bottom of the storage system, whether we are using centralized or distributed. After RAID or replication is implemented, we have our physical volumes, which are created on top. After RAIDing or replication, we have our physical volumes, which are created on top of our centralized or distributed physical disks. So in most cases, the physical volumes are not directly mounted to the upper layer applications, for example, the operating systems or virtualization systems that we have been using as examples in this document. And the reason is that once a physical volume is mounted, all its space is formatted by upper layer applications. So after the storage space is used up, you can add disks to expand capacity. However, you need to reformat the physical volume after the capacity expansion, which may cause data loss. Therefore, typically, multiple physical volumes are combined into a logical group, and then the volume group is virtualized into multiple logical volumes, which we are calling the LVAs. So the upper layer applications use now the logical volumes to access their data. So we are saying in cloud computing, the virtualization program formats the logical, our virtualization program, for example, Fusion Compute or VMware EXI or Fusion Sphere or Hyper-V or any other application that you're going to use to virtualize your virtualization solution. They're going to actually format this logical drive, but not the physical drive, because vendors use different virtual file systems. And we're saying, for example, VMware uses the virtual machine file system, the virtual machine file system, the virtual machine file system by VMware, virtual machine file system by VMware, and Huawei uses the virtual image. Huawei uses the virtual image files. Sorry, we uses the virtual image or the virtual image manage system, which we are calling VIMS, the virtual image manage system. So both of them are high-end performance cluster file systems that deliver high capacity exceeding the limit of a single file system and allow multiple compute nodes to access an integrated storage pool. So the file system of cloud computing cluster ensures that no single server or application software have complete control over access of the file system. So if we are using VIMs, it is based on SAN storage. So Fusion Storage delivers only non-virtualized storage, non-virtualized storage space. So Fusion Compute manages virtual machine images and configuration files on VIMs. VIMs uses distribution locking mechanism to ensure read and write consistency of data in a cluster. The minimum storage unit used by virtualization programs is what we are calling the logic unit number. I felt it important to go through these things, so kindly take note of that the minimum storage unit used by virtualization programs is what you're calling the logical unit number, or which you're calling the LUN. So logical unit numbers correspond to volumes those logical volumes you have seen. Volumes are managed objects in the storage system. Logical unit numbers are external presentation of volumes, and logical unit numbers and volumes are located from the same resource pool. So when we use virtualization, logical unit numbers can be divided as thick loan, and we're going to look into that, or as thin loan, and we're going to see what's the difference between those two. And we are saying, as a traditional type of logical unit numbers, thick loans support virtual resource allocation. They are easy to create, expand, and compress. So a thick loan gets full storage capacity from the storage resource pool once it is created. So namely, the logic unit size equals to the allocated space. So if you are using thick loans, usually our computers, when you create a partition, you use a thick logic unit number. If you go to your disk and you say partition, and either you shrink or expand, or you allocate a given amount of storage to that partition, to that logic unit number or logical drive, actually you allocate, it consumes all the storage that you have allocated to it. By default, usually most times we are using what we are calling a thick logical unit number, and we are going to look at that later on. Okay, we're going to be able to look at that later on. So, and we are saying here that the performance of a thick loan is relatively high and predictable. Aside from thick loans, thin loans support virtual resource allocations. They are easy to create, expand, and also compress. So initial capacity allocation policy is set during the creation of thin loans, and after thin loans are created, the storage system allocates and retains the remaining capacity in the storage pool. So when the usage or allocated capacity reaches a threshold, then the system allocates a certain amount of capacity from the storage pool to the thin loans. So this process repeats until thin loan reaches the preset full capacity. Therefore, thin loans have higher storage capacity utilization, and we're going to be understanding why they do have that. So let me go to that slide where we are. This is just a process of creating the thin loan. We looked at those things, and also we are looking here at the process of mapping a file to the disk. So you create your file, the file system handles it, and then it does the mapping via the file system blocks. When the mapping goes to the logical locations, and then boom, to our physical locations on the disks, and then we have our disk sectors. So I want us to take a lot of time on that slide, and let's try to now understand the different virtual machine disks which have been which I'm going to be talking about in the next slide. But let us also try to understand those things. So we are saying that the thin logical unit numbers have higher storage capacity utilizations. So what are some of the key differences between thick and thin logical unit numbers? So we have capacity. So when you're using thick, I've already said, once it is created, it gets all the full capacity from the storage pool. And we are looking at thin. When thin is created, it gets the capacity on demand, the exact files that it needs to run, and then the thin loan is allocated within an initial capacity. When you're creating it, will be like, maybe you can start with the 2 GBs, but then it will keep on expanding and expanding as you need it will expand on demand. If you put on more files, then it expands until when it reaches the threshold. So when created, and then it's allocated with more capacity dynamically. So think of it as it is dynamic. So it keeps on expanding and expanding based on the usage or the demand. So also let's look at space reclamation. So space reclamation here refers to releasing the capacity of some logical unit numbers to the storage pool for the use of other logical unit numbers. So we already know that when you create a thick logical unit number, it takes up all the storage. So this means that capacity reclamation does not apply to a thick logical unit number. So as it gets full capacity from the storage pool when created. So though data in a thick logical unit number is deleted, even if you delete that data, the allocated capacity is occupied by the thick logical unit number. We are saying that if you create your capacity on your hard drive using a thick method, or when you assign it as a thick logical unit number, even if you delete files from there and you have like more free GBs, that data will not be dynamically reclaimed, so that other logical unit numbers can use that data. Okay, so if the thick loan is deleted manually, its capacity then can be reclaimed. If you go back and you delete the partition, then you can actually claim that data. So meaning all that data has to be first to be lost, then you can be able to reclaim the space available on that logical unit number has been using. So when data in a thin logical unit number is deleted, space in the thin logical unit number can be released, because remember it expands dynamically and it expands based on the demand. So in this way, storage capacity can be used dynamically. That's also improving the rate at which you are going to be utilizing your storage or space available. And in terms of performance, we have already said that a thick loan delivers higher performance, and a thick loan is somehow, because it requires some kind of time. And
Samuel.
Yes, please.
Yeah, we are only seeing the content slide.
You're only seeing, yes, because I was just talking about thin and loan. We have not yet, yes, we have not yet go, but we're going to come there in a short while. We're going to go to the next slide in a short while. We don't have these slides available, unfortunately, but I felt it important that I hint some of them, though we are going to talk about them when it comes to the different virtual machine disks that are used by virtual machines. Okay, so here we are saying
we thought it was a network issue.
It's a lot of information. You have this information in your material, so you can as well as go back and you read through it. All this material, this information is available for you. So that's why I'm perusing through, and I don't want to spend a lot of time going through paragraphs.
Okay.
So we are saying in terms of performance, the thick is better than the thin logical unit number. And in terms of application performance, we use thick logical unit numbers in terms if we need higher performance, or when we are not concerned so much about space utilization, and also when you're not really sensitive about the costs or the costs that are going to be incurred, we can choose to go ahead and use that. So if you want moderate performance, we can choose to use thick. And if you want space utilization, remember we said this expands dynamically. And of course, if costs are sensitive because you're utilizing the space, we can now choose to use that kind of that. So we are saying virtualization cluster file systems or common file systems include NAS. We have already talked about that. And basically, I think that is it for now. Okay, right. So let us look at the virtual machine disks. So we are saying that the virtual machine consists of different configuration files and disk files. Please take note of that. A virtual machine, we have already talked about that. It contains of different configuration files and disk files. Okay, and each virtual machine disk corresponds to a disk file where user data is stored. So basically, disk files, it is where what we use to store our different user data. So if a virtualized storage is used, all disk files are stored in the shared directory or the file system. And if we have used a non-virtualized storage, each disk file corresponds to a logical unit number. From the perspective of users and operating systems, either files or logical unit numbers are the same or as common hard drives, which are displayed as hard drives among other hardware resources of the system. That is if you're using a non-virtualized environment. So when the administrator is creating a virtual machine, he needs to create virtual machines of where they'll store their data. He needs also to think about, as I'm creating this, I need to create the disks for my virtual machine. So disk information corresponds to different or several lines in the configuration files. So in the user view, you can either use the user view and you can be able, for example, if you go into your disk management in Windows, you can be able to see the disks that are available on your computer, or depending on the operating system you use, if you're using Windows, you can use diskpart, or you can use disk on a Unix operating system for you to be able to see the different resources that are available to you all at your disposal. Okay, so we are saying that these are, take note of this slide. Kindly take note of the things I tell you to take note of. So we are saying that common virtual machine disk formats, usually most of the different vendors support RAW, and VMDK is supported by VMware, and VHD is supported by Microsoft Hyper-V and Fusion Compute. So you're saying Fusion Compute supports VHD. This is just a file format. File format, like you see, file format for a song is .mp3, a file format for a document is .doc, a file format for text is .txt, and so on and so forth. So these are the different file formats for, or that can be supported by the different vendors, different virtualization solutions. So we're saying VHD is supported by Microsoft Hyper-V, and we're saying also QCOW is supported by KEMU or KVM virtualization platforms only. So meaning if they ask you what formats can be supported by Fusion Compute, already know that Fusion Compute also runs or can run on top of a KVM or KEMU. So meaning already it supports VHD, it supports QCOW, and also it supports this QED file format. And then Oracle VirtualBox supports VDI. Okay, so if you go, actually, if you have your computer and you go to where you store your virtual machines, remember we said they're either stored as disk files or configuration files, you'll actually be able to see, you'll be able to see the different, just a moment, you'll be able to see the different file format. We have already said virtual, this is VMware, okay? And VMware here is supporting the VMDK. This is the file extension. So I created my virtual machine, which is Kali Linux.vmdk. Are you able to see my screen?
Yes.
With my Explorer window, not
Yes,
the presentation.
we can see.
Okay, with the Explorer window.
Yes.
Okay, all right. So if it was Oracle VirtualBox, let me see here. Okay, just a moment. I think I removed it. If it was Oracle, you would see that it supports VDI file extensions. All right, so those are some of the kinds of what was I saying? These are some of the common disk formats that are supported by the different vendors. Okay, so let us try to look at the storage features of Huawei Fusion Virtualization product. So we are saying Fusion Compute can use the storage resources from dedicated storage devices or even the local disks of hosts. So dedicated storage devices are connected to hosts through network cables or optic fibers. We have already looked at some of them. So we are saying Fusion Compute uniformly converts storage resources into data stores. So after data stores are associated with hosts, virtual disks can be created for virtual machines. And we shall look at that and be able to understand the process of doing that practically when our environments are created. So we already said that we can, in Fusion Compute, you see we have here either NAS or SAN, and we have also here the Fusion storage block. And we are saying that Fusion Compute can use some resources from either dedicated storage devices or local disks from hosts. Let's say if it was going to use distributed resources, okay? And we are saying here that storage resources that can be converted to data store include that from SAN, logical unit numbers on SAN devices, including iSCSI storage devices and fiber channel SAN storage devices. So it also supports file systems created on network attached storage here, NAS. It also supports them, and also storage pools from Fusion Block. Fusion Block is the storage solution offered by Huawei, and also local disks on hosts. That is in a virtualized environment or from a distributed kind of storage system architecture. So in Fusion Compute, these storage units are called storage devices, and physical media that deliver storage space for virtualization are called storage resources. Okay, so we have our storage resources here, and we have already said that the ones that Huawei is supporting, and we have our storage devices. Now, after we get our storage devices or the logic unit numbers here, which we are calling our storage devices now, which we are getting from here, and then we create our data store for either our non-virtualized storage or for our virtualized storage. Okay, so before using the data stores, we need to manually add data storage resources. We need to manually configure where are we going to get our resources. Are they from distributed hosts? Are they from block level kind of systems, storage systems? So if the storage resources are IP SAN or Fusion storage here or NAS storage, you need to add storage ports for hosts in the cluster, and also use, and we're going to see this practically shortly after, to communicate with the service ports for centralized storage controller or the management IP address for Fusion Compute Manager. So if the storage resources are provided by fiber channel SAN, you do not need to add storage ports. So adding storage resources, you need to scan for these. When you're adding the storage resources, you need to scan. In Fusion Compute, you need to go there, and we shall see how you can be able to scan for these storage devices on Fusion Compute portal, and then we add them as data store. So data stores can be either virtualized here or they can be non-virtualized. And we can use logical unit numbers as data stores and connect them to virtual machines from SAN without creating, if you're using SAN, without necessarily creating virtual disks. So this process is called raw disk mapping, the RD. If you're going to use the logic unit number to connect directly, and we use SAN, we're going to use raw disk mapping. So this technology applies to scenarios requiring large disk space, for example, database server construction. So the raw disk mapping can be used only for virtual machines that run certain operating systems. Okay, so let us look at some of the characteristics or the features of virtual disks, of Huawei virtual disks. So here we are saying, after adding our data stores, we can create virtual disks for virtual machines, and customers may have various needs for using these virtual machines. For example, they may want to share a virtual machine disk to save more physical space, or so Huawei virtual machine disks are classified into different types based on the requirements. So we can, based on the sharing type, so virtual machines are classified into as non-shared disks and shared disks. You already now get the difference between shared disks and non shared disks already, even before we talk about them, isn't it? We are saying that non-shared disks, okay, or sometimes we call it common. These are non-shared disks. So non-shared disks can be only used by a single virtual machine. So with common, or here if you're looking at the type, if you're looking at common or non-shared, only a single virtual machine. Only a single virtual machine. And if you are looking at shared, you already hear the name shared, a disk that can be used by multiple virtual machines. So if we are going to base on the configuration mode, we have now common, thin provision, and we shall also look at another one called thin provision, lazy. We shall look at it and understand, or thin provision, lazy. We shall look at it later and understand what we are talking about. So here we are saying that virtual machine disks can be classified as common disks, here common disk, or as thin provision disks. And sometimes there's also what we are calling the thick or thin provision lazy zeroed disks. So what do we mean by common? That when we are using the configuration and we configure it to common disk, the system allocates disk space based on the disk capacity. So during the creation of this disk, the data remaining on the physical device will be zeroed out. The performance of the disks in this mode are better than that in the other two modes, but the creation duration may be longer than that required in the other modes. So think of this, it is also sometimes called the thick mode. Okay, so we have our thick and common or thick, and we are saying here all the space available will be zeroed out. The space available on our physical disks or the capacity will be zeroed out. Okay, so the performance of this disk in this mode is better than the rest, and we're going to see why. So here, if we configure with thin provision, we are saying that the system allocates part of the configured disk capacity for the first time and allocates the rest disk capacity based on the storage usage of the disk until the configured disk capacity is allocated. In this mode, data stores can be overcommitted. And we are saying, please take note, it is recommended that data store overcommitment rate should not exceed by over 50%. It should not exceed by over 50% of that storage. And we are saying if you have a total capacity of 100, who can get the answer? How can we overcommit this thin provisioning disk? What should be the maximum capacity if you have 100 GB? Someone give it a try.
150.
It should be 150.
150.
Yes, and the reason why it is 150 because 50% of this is 50. So if we are overcommitting and we have 100 GB available, we should not overcommit beyond the 50%, which is now 150 GBs. So if the allocated capacity is greater than the actual capacity, the disk is in thin provisioning mode. So we also talked at, let me clear this. We also talked at the thick provisioning lazy zeroed. So this system allocates the lazy zeroed here. Let me try to write it. Thick. I'm using a mouse to write. I forgot my writing pad, so you forgive my handwriting. Thick provisioning, lazy zeroed. Thick provisioning, lazy zeroed. And we are saying the system allocates disk space based on the disk capacity. However, the data remaining on the physical disk is zeroed out only on fast data right of the virtual machine as the virtual machine or from the virtual machine as required. So here, when you create that disk, what we are trying to say that the system allocates this space based on the capacity. But however, the remaining or the data remaining on the physical device is zeroed out only on the first write from the virtual machine as required. So in this mode, disk creation speed is faster than that in the common or the thick mode. So the input and output performance between common and thin provisioning modes, this configuration mode only supports virtualized local disks or virtualized SAN storage. So what you're saying with this kind of provision, what it does, it will not zero out the capacity from your underlying physical volume. What happens, it will zero it down the moment the virtual machine starts writing on the logical volume. Then it will now take up, if you configured it to be 100 GB, it will take up all the 100 GB and it zeroes out the capacity from the physical devices. So also let us look at if you're going to configure or create a disk based on the configuration mode or on the disk mode here. So also we are saying that disks can be classified as dependent disk, independent persistent disks, and independent non-persistent disks. So by dependent, we mean that disk is included in the snapshot. Changes are written to disk immediately and performance. Take note of this. When we create it in this mode, we are meaning as they are taking a snapshot, and we're going to look at what's a snapshot when we come to the virtualization features. So we are saying that when we use this kind of disk mode, that our disk will be included in the snapshot. And after we have it included in the snapshot, also what we should take note of that changes are written to disk immediately and permanently if we are using this mode. However, if we are using independent and non-persistent mode, this one here, disk changes are immediately and permanently written into the disk, which is not affected by snapshots. And when we are looking at independent and non-persistent, this one here, we are saying that disk changes are discarded after the virtual machine is stopped or restored using a snapshot. So there are some of the key differences from those. So if you are saying if you select independent, persistent or non-persistent, the system does not take snapshots. So if you select these things here, and you create your virtual machine using this mode, we are saying that the system will not take snapshots of the data on the disks when creating the snapshot for the virtual machine. So when the virtual machine snapshot is used to restore a virtual machine, the virtual machine disks are not restored if you use this mode to create your virtual machine. So after a snapshot is taken from a virtual machine, if disks on the virtual machines are detached from the virtual machine and are not attached to any other virtual machines, the disks will be attached to the virtual machine after the virtual machine is restored using a snapshot. So however, data on the disks will not be restored. So if a virtual machine is deleted after a snapshot is created for the virtual machine, the disk will not be attached to the virtual machine after virtual machine is restored using the snapshot. So we are saying that some types cannot be changed once they are set and some can be changed. So some disk modes also can be converted to other disk modes. And ladies and gentlemen, so this brings us to the close of our storage virtualization basics. And let's look at this simple quiz here. And we're asking, which of the following disk types is recommended for an archive ROM? For an archive ROM that needs to store large amounts of data that will be accessed infrequently over long periods of time. So could I get someone tell us, and you also tell us why you think that answer is that? Maybe you can just say mic check and say it out, or you can put up your hand, anything that you feel comfortable with. Anyone?
I think the answer will be C, SATA disk, because SATA disks store data over a long period of time.
Okay.
And here we're looking at archiving the data in large amounts that won't be accessed frequently. So yes, I go with SATA because of the fact that it stores data for a long period of time. Yes, SSD may have more data storage than SATA, but we're looking at, we can also get a large SATA disk and store it over a long period of time. So I go with C.
Okay, that is Emmanuel. Thank you, Emmanuel. You go with C. Anyone else?
I would also go with SATA because SSDs don't work over a long period of time. They don't, how can I say? They get spoiled easily, quickly after a certain period, I think. So
Okay.
yeah, going with SATA.
Okay. All right. So I think those are enough. Let us also, yes, Kwesiga, you had a submission. I saw you unmuted your mic.
Yeah, I wanted the people who are submitting to relate, because definitely SSD is out of the picture since we are looking at something for archiving. So even its cost and everything, and being archiving, SSDs have short lifespan. So I want someone to tell us why they are choosing SATA, not SAS and not NL, because these are all HDD. I think that's where the discussion should be. Of course, SSD is out of the picture, yeah.
All right. So do you want to first give it a shot before anyone else gives it a shot?
To me, my submission would be also SATA. Reason being, when you're looking at SAS, you're looking at higher performance. Yet here we are not looking at frequent access of data. Then the NL combines, of course, both SATA and SAS. That's why we get the NL. So I feel like we don't need to go into all those complexities if we just have the SATA, since it's just an archive.
Okay. All right. Anyone else? Someone from the chat, Peter, is saying SATA store data for long periods. SSD have short lifespan. All right. Okay, so let us look at the next question. Thank you so much. I'm not going to repeat what you guys have said. I think you have exhausted that question. So SATA disks use parallel interface, while SAS disks use serial interface. True or false? Someone is telling us false. Why?
False.
I'm saying Stephen, why?
SATA in full is serial.
Okay. Cynthia, you unmuted your mic. Did you want to say something? Okay. All right. So that brings us to the end of this chapter. And I want to say that today is Tuesday, and I want us to do our first set of mocks. That is on Thursday. Okay, that is on Thursday. That is on Thursday. That will be 8th, and then we shall do our second. Are you guys okay doing something on a public holiday?
No.
No. Who is
No.
this? Oh, is
No.
that?
I have a submission to make.
But okay. Yes, Kwesiga can go ahead and
I thought the course was planned for 2 weeks, Monday to Friday, in
yes,
advance.
yes,
So
it was.
when we start arguing of whether we shall have something on Friday or not, so my question is, where do we fall after that?
Where?
Where do we fall after that? Because to me, according to the program, the course is supposed to end on Friday.
Yes, the teaching is supposed to end on Friday. Originally,
Exactly.
on Friday, originally, yes, that the training and the teaching. Then, but according to me, my personal plan, I was thinking that you should be able to do the exam on Friday, this Friday. But one, it's a public holiday, but it's not only a public holiday here in Uganda, but also it has been a public week in China. Let me stop recording.